Hi, I'm Mike Seaman for Eta One Power, and I'm here to show you our new product, Eta Designer. This is a new program which enables power electronics engineers to conceptualize, design, optimize, and analyze their power converters in one place. Let's open the program and see what it can do. Eta Designer opens with a schematic editing window. Here you can draw any circuit you want, but let's start by designing a traditional buck converter. We've actually implemented a new wizard that allows you to design a standard topology without having to draw each individual component. So let's design a new 5-volt down converter. So we'll start with the input of 8 to 24 volts, have an output of 5 volts, and then an output current from 0 to 10 amps. We'll click Next, and Eta Designer shows a number of supported topologies for this conversion ratio. For each of these, it'll show the schematic and a brief description. And for this example, we'll just choose a simple buck converter. The next step is to specify the switching frequency. Here we'll specify 500 kilohertz. We'll click Next and then Finish. And then now we see that we have a fully specified closed loop buck converter. We can run a transient simulation by selecting transient simulation, and just like that, we have a startup transient simulation of this converter. Eta Designer's focused around an incredibly fast simulation engine that allows you to perform advanced simulation and optimization functions without having to wait for them. So this startup looks okay, but I think we can get a better transient response. So let's take a look at the controller. If we go into the controller block, we see that it's a very flexible design. What it allows you to do is specify inputs to the block. So for example, we're measuring the output voltage, and then specify PWM outputs. The way that each output is specified is down here, so we can see the waveforms. We can drag the edges back and forth, and then specify constraints on each edge to ensure that the PWM does exactly what we want to do. So for example, this edge here is set as a 20 nanosecond delay after the falling edge of the low side waveform. And that's your traditional dead time. We see we have a period constraint on this edge, and then finally this edge is set as a filter compare. What does that mean? So the PWM will turn off when the loop output, this is the compensation filter called V-loop, is less than the PWM. So that's a traditional voltage mode control. So let's look at the filter compensation. So here we can select between a proportional filter, a PI filter, and a PID filter. By selecting each of these filters, we see the Bode response. We could also take a look at how to implement this converter using an analog feedback loop or difference equations in case we do a digital controller. Next, we can see the transient response of the filter in real time, and we can tweak the values. For example, here we're increasing and decreasing the DC gain, and see the crossover point and the total loop gain change in response. But this doesn't give us the transient response. So actually what we can do is specify variables here. So for example, I'll change the gain to a variable called gain. I'll call this 0 FZ, and I'll actually move this pole to 10 times FZ. So just like that, we can specify variables and then see how the loop response changes as we change the variables. So let me close this, and we can go and define these variables. So I'll add 2 variables. The first one called gain. We can specify an optional description, copy and say Ator gain, and we'll set this to 50K, but set it as a range, so we can go from anywhere from 5K to 500K. And this gives us enough room to investigate how changing that variable will impact the circuit. So we'll do the same with the 0 frequency. I'll set that to 30K and have that range between 10K and 100K. So click OK. And now we see that a transient response is updated with those variables. But what Eta Designer allows you to do is sweep those variables in real time and see how the response changes. So for example, here we have a list of variables. So we can take a look at what happens when you sweep the output current. And you can see that the inductor current changes directly with response to the output current. And the output voltage stays pretty steady. You can do the same thing with the input voltage as well. But that's not what we're looking for. Let's see what happens when we adjust the gain. So as we turn up the gain, the response becomes faster. As you can see, the current waveform here, the response becomes faster and eventually becomes unstable. So we'll back it off a little bit to about there, and maybe now we can tweak the zero frequency to see if we can get a better, more stable response. So let's see. And doing this over multiple variables allows us to get a very good response. So that looks like an excellent response, much better than what we started. So I can close this window, and it lets us save the new variable values back to the schematic. So I'll click Save, and there we go. So that's an optimized control loop. Now let's take a look at circuit efficiency. So here we have idealized models for each device. So the transistor, for example, has on-state resistance, a saturation current, a diode forward voltage and resistance, and an output capacitance. But let's actually convert this to a library component, which allows us to specify a model from a specific real device. So I can click this, and now I can select devices from our library. It automatically places a filter that allows us to look at devices with an appropriate voltage range. So not only does it let you select a model, but before you choose a model, it first of all gives you the price of the part. It also substitutes the part into the circuit and shows the efficiency of the circuit. The efficiency isn't necessarily valid quite yet because we haven't defined the other components in the circuit, but at least gives us a zeroth or a first order approximation to the performance of each part. So let's go ahead and choose parts for each of these devices. And we can do the same thing for the inductor. Oops, so we have nothing visible quite yet. So let me go ahead and just close the filters, and then we can see all the parts that are available in this version. Later releases of Eta Designer will have a much larger component library available. So let's choose this inductor right here. Okay, so now we have our converter. It still simulates just as fast as it did before, still looks stable. And now we can take a look at efficiency. So we can plot efficiency over output current and see that, well, it's actually quite good here. So we get close to 98% efficiency from this converter, and that's actually pretty good. But let's take a look at where these losses come from and what happens. So actually one thing I'll point out here is you actually see a little hump here, and that's due to the circuit going into discontinuous mode at lighter current levels. And Eta Designer, because it takes efficiency from the actual waveform, it actually incorporates that into the efficiency calculation without you having to do anything. So let's take a look at where the losses come from. So we can do an efficiency breakdown. And here you see that the losses come from a number of different places. So we have M1, M2, those are the two transistors. U1 is the controller, and it's also the gate driver. So any gate drive loss gets incorporated into U1. And finally, the inductor L1 is shown here. It includes both the DC resistance loss and the core loss. Now we can see, as we vary the input voltage or any of the other variables, how the efficiency changes. This allows us to figure out which components dominate the loss, and also what things you can do to improve the efficiency or the performance or the cost of the circuit. So that's a quick look at Eta Designer. There's a lot more features in here that allow you to optimize your power converters. So I'd like to thank you for your attention and hope you enjoy Eta Designer.